Okay guys, so this is, you've all sort of handed this in from my group, but I thought I'd do the video with you again and go over it. I know I went through question 3, the third one of those, with you on the Zoom tutorial that we had, but I also thinking about the other group as well, and groups in the future that will be doing this, so I thought I'd go through the 3 questions again. Okay, so the first question, so I'll do the first one first. Well, obviously I will. I've got a couple of colours here. Oh, let me put the pens in. I'll just use black and red for today then. So question 6, a car is towing a trailer along a straight line by the means of a tow rope. The mass of the car is 1,400 kilograms. The mass of the trailer is the car and trailer modelled as particles blah, 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 blah. Due to the engine is to the find the acceleration, the tension in the tow rope. Okay, so what I'm going to do is I'm going to draw a diagram. You should always sort of do this, and then I'm going to put all my forces on. So there's the thing, there is the rope, there's the car. Not my best drawing of a car. Let's put some wheels on it and a wheel on the trailer. And I'm going to put all of the information, the mathematical information on that. So the mass is 1,400, and I hope I don't make any mistakes of this because I'm reading this for the first time. I haven't done this before. The resistance to motion for the car and the trailer are assumed to be constant. So that means it's 630 newtons, and we've got 280 newtons for the trailer. Okay, acting back, there's a tension in that. So the tension acting is tension that's pulling along the trailer, and it's resisting the truck. The driving force of the car due to the engine is, so that's got a driving force of 2,380 newtons. That's what the engine is producing. Find the acceleration of the car. Okay, and the tension in the tow rope, and then there's some other stuff to look at in a second. We'll do that in a second. So so the acceleration of the car, so we're going to apply F equals ma. So remember the F here is the net force, and the net force is the 2,380, but you've got to take away the forces that are acting against it. So 630 plus 280. Okay, so that's all of the net force, isn't it? That take away those 2, and that is equal to the mass of the whole thing. We're considering the whole thing. So 14 adds, that is that. Did that in my head, so I'm quite proud of that. Times the acceleration, which we don't know. So it's all that just divided by 210. Let's do that on our calculator. 2,380 minus, in brackets, 630 plus 280, close brackets, is equal to that divided by 2,100 is equal to 7/10. So the acceleration is 0.7 meters per second squared. Okay. The tension in the tow rope, so this is where we split it and just consider one. So now what I'm going to consider is the trailer. Why? Because it has less forces acting on it. It has the tension pulling it. It has a force of 280 acting that way. It has, I don't know why I've switched to 700 kilograms mass, and it's got an acceleration of 0.7, which is just above, isn't it? Okay, so applying F equals ma to that. The force is the tension minus the 280, so that's a net force, isn't it? Is that take away that? That's driving it, is equal to its mass, which is 700, times the acceleration, which is 0.7. So the tension is 700 times 0.7 plus the 280, rearranging that formula. Simple as that. So let's do that. 700 times 0.7 plus 280 is equal to 770. So the tension is 770 newtons. There we go. So we've got A and B done. All right. So we've got, let's just put those in because I need those, I'll put them up here. I need to clear some space, and the acceleration was 0.7 meters per second. This will be off screen for you, so you won't be able to see it, but I've just written those two values down for me. And then there's a next bit, so let's read that. When the car and trailer are moving at 12 meters per second, the tow rope breaks. Oh dear. Assuming that the driving force on the car and the resistance to motion are unchanged, find the distance moved by the car in the first 4 seconds after the tow rope breaks. Okay. All right. Okay. So the tow rope has now just snapped. Oh dear. And the car and trailer were moving at 12 meters per second. So they reached 12 meters per second to the -1 and snap. That happens. Okay. Once that happens, then things are going to change, aren't they? Okay. And what's going to change is that the resistant forces, that is the tension, has gone. So the only forces now are that 630 newtons, 1400 there. We've got 2380. It says that doesn't change. So what will change now, of course, is the acceleration. This will start accelerating faster. Okay, because it's having to, it's pulling less if this force stays the same. So let's recalculate the acceleration first of all. That's why there's 6 marks for this. I've got to do this in a couple of stages. Okay. So if we apply F equals ma to this situation now, the force is 2380 minus 630 is equal to the mass, which is 1400 times the new acceleration. So that, take away that, divided by 1400 is the acceleration. Going to this, 2380 net force minus 630, that's the net force, is equal to that, divided by 1400 is equal to 5/4. So you can see quite a big increase, 1.25 meters per second squared. That's the new acceleration. Okay. And what do we want to do? We want to find the distance travelled by the car in the first 4 seconds. So I'm going to use S equals ut plus a half a t squared. I'm going to use that one because I want to find, it has to have an S in it, has to have the initial velocity in it, which we've got, because it had reached 12, we've got the new acceleration, and we've got the time, which is 4 seconds. So I'm just going to stick the numbers into that. So the distance travelled is going to be 12, so we're starting at 12 meters per second for 4 seconds, plus 0.5, that's just my half, times 1.25 times 4 squared. Should be right, and that should tell us how far it moves in that time. So 12 times 4, I can do that in my head, by the way, plus 0.5 times 1.25 times 4 squared, 16 is equal to 58. So S is equal to 58 meters. Sorry, I didn't look at the pens there. It's gone black, red, black. Okay. And state how you've used the modelling assumption that the tow rope is inextensible. So there's always one of these, either about friction or... So one of the assumptions that you always make in mechanics is that, ropes or rods or tow bars are non-elastic. Because if there was stretch in that tow rope, then it would affect the tension. So you just have to make a statement saying, the tension is not affected by the fact that it's non-elastic properties in the rope, or just use that word again. The rope is inextendable, which means it doesn't affect the tension. Okay. It's not in that last bit, but it's obviously in the earlier question. Okay. Hope that was okay. Hope I got them right as well, and that's what you got for that. I'm worried about making a mistake because I often make mistakes, as you know. Okay, so let's get rid of that and let's have a look at question 2. It's actually question 5. The actual number, by the way, is 6. So, that's quite a, this is taken from an AS paper, and they only ever have, the old M1 papers, they only ever have about 7 or 8 questions. So 6 tells you, it's getting on to like a grade B question, because they do put the easier ones first and then the harder ones at the end. A question 5 is a grade C-ish sort of question at AS, not at A2, but at AS. Although this looks fairly sort of straightforward. Okay, oh dear, no, it's quite a lot of marks for this one. Okay, so let's have a look at it. A ball is projected vertically upwards with a speed of 21 from a point A, which is 1.5 meters above the ground. Okay, so that's why it's so always draw yourself a diagram. Ooh, and down here. Plonk. So there's my diagram. That's what's happening, up and then down. And we just do it, don't we? So it moves over a little bit so we can see the path. It's actually going straight up and straight down, so it's someone to have to lean over and lob it up. Okay, we're going, always put that on. U is equal to 21 meters per second. Squeezing that out, so 21. And because now we've decided up is that, then gravity in our equations is acting down, so we're going to use that as minus 9.8. Okay, so just be careful with that. Remember at the top, a real key point here is that the velocity is 0, because it slows down, stops instantaneously and then speeds up again. So that's an important point that is always used in these questions. And this distance here is 1.5. In reality, what does it mean? It means that S is 0, the start. This here we're going to use as S is equal to minus 1.5, because remember down we're saying is negative, up is positive. So we have to, from those lessons, remember you have to pick your direction. So we're using S as minus 1.5 at this bottom point here. Alright, so let's go. A. We'll do A here. The greatest height above A reached by the ball. So it's above the platform, not above the floor, so we don't have to add on 1.5. You always get this question. The greatest height, so we want V squared is equal to U squared plus 2AS. Using that version of it. I use V equals U plus AT if I wanted to find the time to the greatest height. But I'm going to use that to find the actual greatest height. Velocity, of course, is 0. 21 squared plus 2 times minus 9.8 times S. Okay, when we take all of this over, this is minus 19.6. When we take it over to that side, we get 19.6 S is equal to 21 squared, which is 441, and divide by 19.6. So 21 squared, just check, divided by 19.6. is 22.5. They often use, by the way, in these questions an initial velocity of 21 because it's a multiple of 9.8, so it always seems to work then. Well, it always works out with reasonably nice numbers for you. They do that on exams, they do it in the textbooks as well. So 22.5 meters. Let's get our units on the homework. Some of you are missing off your units. Okay, so try to get into the habit of putting those on. That's the first one. The speed of the ball as it reaches the ground, that's that point there. So we want V there. Okay. So remember, when it hits there, the V is going to be negative. You know, it's coming down, so it's a negative V. We don't need to put it as an answer, express it as an answer of it being negative. It just says the speed, so we don't have to include the direction for the velocity. So B. So we can go S is equal to UT plus a half AT squared. No, we don't want to use that. Talking absolute rubbish. V squared equals U squared plus 2AS again. That's what we're going to use, everyone. So the velocity squared is equal to the initial velocity squared, 21 squared, plus 2 times minus 9.8 times minus 1.5. Because that's that point there, it's at the point minus 1.5. We want to find the velocity when it's at minus 1.5. When we put that in to the equation, the minus times the minus is a positive. So we end up with v squared is equal to 21 squared, which is 441, plus 2 times 9.8 times 1.5, which is equal to 470. And I'm going to put that in now, because actually when you square root that, of course, how do you do that on here? Oh yeah, there you go. You get 21 point, and I'm just going to round it off, 7 meters per second to the minus 1. But of course, because you've square rooted it, you get plus or minus. The positive value of that would be at this point here. It would have started off its life, had it been projected from the floor, at 21.7. Gravity would have slowed it down to 21 once it had reached a height of 1.5 meters, which is where it's actually starting from. You know, the question itself doesn't know that it's a real life situation. You know, this is just a quadratic equation, and so this is in at a minus a negative time. Okay, so the velocity is the negative one that we want here, but so it doesn't matter because we're just given the speed. The speed is 21.7 meters per second to the minus 1. We only need to know that it's minus for when we're substituting into, you know, equations. And then C is the time taken the instant the ball is projected from A and the instant when the ball reaches the ground. So C is using that S is equal to UT plus a half AT squared. Okay. And again here, S, be careful, we're going to go minus 1.5 because we want the time when it's at this point here. It's going to give us a negative time back here, and we want the positive version of that here. Okay, so is UT, so 21 is UT, plus a half A. Now a half A is minus 9.8, so I'm going to go straight in for minus 4.9 t squared. Take everything over to that side and we get 4.9 t squared minus 21t minus 1.5 is equal to 0. That's right, yeah, okay. So that's what we're solving. Not nice, it's not going to factorise, got to use the quadratic formula. So I'm going to go minus b, so minus 21, which is, plus 21. Plus or minus, I'm only going to go plus because I only want the positive time, I don't want the negative time, because that's not in the real life situation. B squared, so the 21, so 441 minus 4 times A, which is 4.8 times C, which is minus 1.5, all over 2A, which is 9.8. So all of that, the minus and minus is going to be a plus. So I'm going to go 21 plus the square root of 441 plus 4 times 4.9 times 1.5, and I put them in as positive because all minus times a minus. So that's all my top row. I'm just going to press equals there, and then I'm going to divide all of that by 9.8, and that's going to give me a sensible time, which is 4.35 seconds. So 4 point, and I'm going to go 4 seconds. Okay. So it took 4.4 seconds to reach there. Okay, and that is question 5C. Yeah. Alright, hope that was okay for you. And then I will go through, because the other group hasn't seen this, I know I went through it on the tutorial with you, I will go through this last one. I did like this question. You know why I like it? Because although some of you struggle with it, there's no special maths in this at all. This is just applying simple maths, and it can be done by just drawing a simple diagram. Okay, but you've got to get used to drawing your diagrams. A particle P is moving with constant velocity of minus 5 plus 8. So first of all, let's just do that little maths up here. So it's going minus 5I plus 8j. Okay, that's the velocity. So it's got the direction. Direction is there, isn't it? That's the direction it's going in. And it's got the speed. Okay, the speed is the magnitude, okay, of that, and we do that by Pythagoras. So that is just the square root of 8 squared plus 5 squared. You know, if you think of minus 5 squared, it's still 25. So 64 and 25 is equal to 89. So it's root 89, whatever that is. Okay, so the speed is root 89 meters per second. First bit done. And the direction, well, if we find that angle there, ignore the fact that it's minus, inverse tan of 8 over 5, tan to the minus 1 of 8/5, opposite over adjacent from basic maths, gives us that angle there. So cancel, shift tan, make sure this is in degrees, it is, of 8/5. Okay, is equal to 57.99. So I'm just going to go 58.0 degrees. So 58 degrees, rounded off to 1 decimal place. But it wants it as a bearing. Okay, so that's why, again, it's good to have that diagram in. You know, a little diagram tells me that there is north, and I want that as a bearing, clockwise from north. So I want 270 degrees plus that. So plus 270, and that gives us 328 degrees. So as a bearing, 58 plus 270 is equal to 328 degrees. There you go. Okay. So that's the basic stuff over with. Okay, 5 marks for that. Direction and the speed. Blimey, that's a generous 5 marks, isn't it? Okay, but here's the real maths. Okay, another 8 marks for this. So, and this is, I like this now. Okay, so let's do this. Here it is. So draw ourselves a diagram. At time t is 0, p is at the position vector 7i minus 10j. So let's put all this information in. 7i minus 10j. So it's here. 7i minus 10j. Position vector point A, so that's point A. It's there. Okay, so I've done it roughly where it would be along 7 and down. It's the coordinates 7 minus 10, isn't it? And that's where it is at t is equal to 0. Okay. When t is equal to 3 seconds, the velocity of p changes, and it moves with a velocity of ui minus, where u and v are constant. Okay, let's just do this first bit. So the question says that's where it is, but it travels. It tells you at the start that it's moving with this velocity. It's moving with this velocity. So that means for the first 3 seconds, when t is 3, it's moved from when t is 0 to when t is 3 by this velocity. So it's moved 3 lots of this. This is a velocity of minus 5i plus hj. That's its initial velocity. It tells you that right at the very start. So it moves that times 3. That's what it's doing every second. So if we times this by 3, it's moved minus 15i plus 24j, hasn't it? Okay, in 3 seconds. So no special maths here. You've got 7i, it's moved minus 15i, so that's going to be minus 8i, and minus 10j plus 24 is going to be 14j. Now what did I say? I said 7i minus 59 is minus 8i. So it's going to be up here now. It's going to be at the point of minus 8i plus 14j. And that's at t is equal to 3. And that's because it's moved that much in 3 seconds. It's gone up to there. Okay, that's at t is 3. Okay. After a further 4 seconds, it passes through, it changes velocity, by the way. So the speed changes, and after a further 4 seconds, it goes through the origin. Find the values of u and v. Okay, so now let's put the path on. Okay, so it's gone sort of up to there, and the second leg it's gone to there, hasn't it, to the origin. Okay, and this bit here, it's done that in 4 seconds. Okay, no special maths here at all. It's just to get back to the origin from there, from this point of minus 8i plus 14j, it's just got to go plus 8i, hasn't it, and down 14j. In other words, it's got to go, it's at minus 8i, so it's got to go plus 8i, and it's got to go minus 14j, and it's got to do that in 4 seconds. So how much does it do in 1 second? Well, divide those both by 4, and we get 2i, and that divided by 4, 7, 3 minus 3.5. That must be its speed, mustn't it? It must be travelling that every second. So just dividing that by 4. So in a further 4 seconds, it's reached there. Okay. So u and v, u is 2, and v is minus 3.5. According to the question, it says what's u and v, and ui plus vj meters per second. Got that? That was for 5 marks. That, blimey. And find that. And what does it say? After further pass through the origin, and find the total time taken for p to move to position A. For p to move from A, from the original A, to a position due south of A. Okay. So it carries on through here at that speed until it's here, due south of A. Okay, so let's say it's at the origin now. So let's just have a look at this leg, because we know it's 3 seconds to there, we know it's 4 seconds to there. From this point, it's got to get down here, so it's due south of A. Okay, and it's travelling at a speed of 2i minus 3.5j. We've just worked out that velocity. Okay, and if it's travelling at that velocity, it does that every second. So how many seconds do we times it by until it gives us something that has, well, look at this, the x-axis of this is 7i, isn't it? Okay, until it has a value of something with 7i in it. When it's got a 7i in it, it's in line with this. Well, if we multiply this out, we get 2ti minus 3.5tj. I'm not interested where it is vertically. Well, I am, it's in 7. Well, I'm not interested in where it is vertically, sorry. I'm just, the horizontal has got to be 7. So 2t has got to be equal to 7, hasn't it? You know, the I bit of this here. So you can see that t must be 3.5 seconds. We don't need to times the minus 3.5 times 3 to find out where it is vertically. We don't need to do that. It's down here, minus 10 point, minus 10 point something j or 11j. I'm not interested in that. It's just, I know that after 3.5 seconds, it's in this line. The question tells me itself it's below it, but it doesn't. We're not interested in that. Okay. So it must take 3.5 seconds to line up again with A, and actually it's due south of A. But the question says find the total time from P, from where it starts. Well, 3 seconds to there, 4 seconds to there, and another 3.5 down to here. So the total time is, what did I say? 3 plus 4 plus 3.5. So 4, 5, 6, 7, 8, 9, 10. 10.5 seconds. Is that right? 10.5 seconds, yeah. That's how long it takes. And all of that was just done by taking velocities or taking distances travelled over so many seconds, because it's all constant velocity, and just chivying it up, into sections to find out the actual velocity and how far it's travelled and so on and so on and so on. it was all just straightforward common sense. Can't really do it without a diagram. And you see all my questions are done, this one, you know, with diagrams, this one with diagrams, this one with diagrams. You have to do that in mechanics to explain it. I can't do it numbsy. You know, I didn't just do it with diagrams because I'm explaining it to you guys. If I was doing it for myself, you know, when I do my own notes, I have my pad here that I do them first before I go through them. I haven't with these ones. That's why I'm a bit worried that I've made mistakes. But I always draw diagrams myself so I understand what's going on, okay, and get all the forces in and get all of the directions and positions in and so on and so on and so on, okay. All right, okay, hope that makes sense, and I'll over and out.